Hello everyone, welcome back to the lecture. So this is lecture 19 and today we will learn about how to write Verilog code for sequential circuit. This will be a quick lecture, so let's begin. So I'm just going to go through quickly how can we uh, describe a sequential circuit using Verilog code, and why I use the word describe because our Verilog or any other language is called hardware description language. So technically it's just describing how the behavior of a circuit in code. So to describe a sequential circuit in Verilog, we need a few things. We need, of course, the clock, right? Because the sequential circuit behave on the clock. Um, so in Verilog, we can actually do some pretty nifty trick, like we can have external lock, an internal lock, or we can have a temporary clock. Okay, that means you can have a clock that just keep running forever, or we can have a clock that basically run for a certain amount of time, or sometimes you can actually make a clock turn on and turn off, like specifically it as your command. So you can do a lot of things when you put it in the software level like this. It's a lot easier than implementing everything in the hardware. Another thing is checking clock edge to perform operation. Checking clock edge is basically, you remember when we went through the D flip-flop exercise, you have to scan the clock, right? And basically the signal or the output is gonna change depending on the clock edge. So either it's gonna be positive edge or negative edge, or in other words, it would be falling edge or rising edge. I mean, rising edge or falling edge. Um, so for example, the good way to check it is use the keyword always. Do you remember this keyword always? We use that when we use the if-else behavioral modeling for Verilog. So this keyword will scan. Okay, it will scan a pin. It will scan a particular pin or a particular signal to see if there's any change. And if there's a change, it will respond to that change. Okay. Uh, Finally, we have to assign a value to the output of the flip-flop within the clock edge check statement. So if you write always, put something in here. That's your code. Okay, so the first example we'll go through is how to design a module, a Verilog module for the D flip-flop, which is our basic memory element. So first we design the D flip-flop with no reset. Okay, so as you remember, you start with module and module. You give it a name. Everything is the same. You give it a name. You put in all of the necessary pins. So there's no reset. So there's only 3 pins, right? You have the data input. You have the Q output. You have the clock. Okay. So the output, let's just Q. Input this. Why you need to write down this reg registers keyword right here is because you are using behavioral modeling. So you need to do this. Okay. So and in this case we will design a positive edge clock. So you can write down pos edge clock. You can have negative edge clock also. Uh, so when positive edge clock arrive, what will happen? This phrase will be executed. So this is not less or equal to. Okay, this is a different thing. This means shift data D to data Q. and AND module. Okay, so we define the output as type registers. Okay, the output is being assigned to its value within a procedural statement. Okay, so every time you use that always statement, or every time you use the behavioral joke, just a reminder, you need to use this registers type. Now the next example is D flip-flop with reset. So everything is the same. Okay, now you add in another input for reset. So I have another input for reset here. And for reset, you need to define either it's going to be positive edge reset or negative edge reset. Okay, so in here we decided to have negative edge reset. Okay, so we have negative edge reset. So in here you can see if reset is if reset is 0, okay, if reset is 0, then you have you basically assign Q to be 0. Okay, so you say everything that is 0, else if not, you shift D to Q. So define output as type of registers the same way. The recess is asynchronous, so it's checked whenever the reset goes from 0 to 1 to 0, so it's on the falling edge. So next we will design a JK flip-flop. Okay, so first of all I want to refresh your memory about JK flip-flop here. Okay, here's a pointer. Okay, so this is the structure of a JK flip-flop. So JK flip-flop is technically the D flip-flop connected to another combination of circuit, right? So in that way you can just write a module like this. You start, everything similarly, module and module. You define all of the necessary input and output. So you have input is JK, okay, input is JK, you have the clock, and also different from this picture, but you also have reset, okay. So and your output will be just Q, okay. But another thing is you have a wire, okay. So for example, I will define this wire as JK, okay. So this JK wire here, okay, is technically my I would say the flip-flop input equation. Alright, so as you remember, like I will write the Boolean algebra expression for this whole combinational circuit here. So I assign JK equal to that Boolean algebra equation. So next, I just have to connect this JK pin into the D flip-flop. So I have a D flip-flop. So this is a keyword defining for D flip-flop I did previously. Okay, it's not given in Verilog. So if you want to use D flip-flop, you need to define it before. So okay, so I write down D flip-flop and I plug in that JK pin as input. I plug in Q as output, and I just put clock and reset. And now I have my JK flip-flop. Okay. Finally, is T flip-flop. T flip-flop is basically the same thing. It's very simple. So basically it's the same thing, but if you go back and review this wire DT here, I use that just similar to the JK wire example. So the wire DT here will be representing for the D flip-flop input equation. The D flip-flop input equation. So that D flip-flop input equation that I need will be So dt right here equal to q XOR t. Okay, so then I would do the same thing. I use that as the input for the D flip-flop. I use Q as the output. Then now I have the T flip-flop. So next we can design a sequential circuit directly with the always if-else case statement without using the D flip-flop as a subcomponent. So let's go through an exercise. Let's try to design a circuit that can detect a new sequence of 0 when it occurs. So let's say I have an input of 1, 1, 0, 1, 0, 0, 1, 0, 1. So what will happen at the output? So every time you see the input flip from 1 to 0, it will output a 1 in here. Okay. So here's the code, and let's quickly go through this. Okay, so there's 3 times that we use the always statement in this code. The first always statement is to check the clock stage and the reset. Okay. The second the second always statement is to describe the state transition. So in order to describe the state transition, you need to scan for 2 things. What is the current state? What is the coming input? Okay. And finally, you will describe the output. And because this is a Billy machine, the output will depend on the state and the input. Okay, first of all, let's go back to the beginning. So in this code, okay, let's remember you have to define all of your input and output. So you have your input, your output is this, okay, and your output is the Y out, your input is X in, and also clock and reset are also your input. Next is when you have X. Okay, so what is missing here is you need some internal state of the machine. So what you need to do is you need to define the internal state. So you can use registers, okay, type to define 2 variables. One is for current state, one is for next state. So since we're gonna work with a 4-stage machine, okay, so we only need 2 bits to represent each state. Okay, so I can define the state as a 2-bit binary number. I can also use the keyword parameter to assign a parameter label for each number. Okay, so I can use S0 to assign for 2-bit 2-bit binary 00. S1 is 01, S2 is 10, and S3 to be 11. Okay, this will be more convenient later in here since you can easily keep track of the name of the state. Of course, you can use auto word too. You don't have to use S0, S1. It's up to your imagination. Okay, so here we can create multiple always statement, okay, to execute different pieces of the code when different input change. Remember that. In this statement here, when to this first always statement, so when positive edge clock appear and negative edge reset, you can, if the reset is equal 0, okay, if reset is equal 0, you will assign the current state, go back to state S0. So this is the reset, the beginning, the initial state. Always reset to this. If reset is not 0, then that means the 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 state will become next day. Okay, current state become next day when next clock cycle come. Okay, so in the next always statement, here is when you perform your state transitions. So you remember you can do case, the case statement here. You do case and case, and you will scan for the current state. So if the current state is S0, then you can, okay, now you think about, okay, current state is S0. What is on of the path? What is on of the decision path that it has? So you scan for, so if, so technically there's only two possible input, right? So xn is a single bit binary number, so either it's going to be 1 or 0. So you can use an if else statement for this. So if xn equal to 1, then you can have next day go to S1. If not, it will come back to its S0 state. So you do the same thing. You do the same thing from S0 to S3. Create all of the decision path that you need for this. Then end case. Finally, and next we will design a test bench for sequential circuit. Okay, so the test bench for sequential circuit is quite simple. So remember, when you design a test bench, the easy trick is just label the whole test bench module exactly the same as your design module, but put the word TB either in beginning or at the end so that you can tell. You have to make some wire for output, registers for the input. Plug all of the pin together. So this statement initial 200 sharp 200 finish means you run this simulation for 200 nanoseconds. Okay, so the initial, so basically everything after that we just try to describe what's going to happen to your test bench. First of all, what you need to do is you need to define an internal clock. For example, if you want to use internal clock, you can define that. So make an internal clock here with the keyword initial, begin, end. Initially have the clock start at 0. Repeat forever every 5 nanosecond. Flip the clock every 5 nanoseconds. Flip the clock value. So pause and ask yourself a question: what is the clock period in here? So the answer is clock period is 2 times of this, so it's 10 nanoseconds. So the clock cycle has time of 10 nanoseconds. Okay. Next is you have to write down the initial, but use the keyword fork join. Okay. So the fork join statement is an alternative to begin end, where unique signal is executed in parallelly. Okay, so trying to have it parallel with this. If you use begin and end, you don't have that parallel execution. So here is how you try to have these two components run at the same time. So you can have one of your reset and input assigned in this module. So this is how you make a test bench. So if it was begin end statement, so the TXin would receive the first value at 12 nanoseconds, so it's like 2 2 plus 10 nanosecond, while in the fork joy statement is only wait for 10 nanosecond. The T reset and TX in can be parallelly executed. This T reset and T in can be parallelly executed. So let's go through an exercise with sequential circuit in Verilog. So let's try to write a behavioral Verilog module that mimics the behavior of a circuit that possesses 4 D flip-flop. Each D flip-flop has an input of D and clock and output of Q. Assume each D flip-flop triggers on positive edge. So let's go through this exercise together. So you start with, let me turn on my pointer. So you start with, of course, writing the module name, giving it a name, and putting all the input and output here. So remember that this is a 4-bit, okay, a 4-bit D flip-flop. So D will be 4-bit and Q will be 4-bit instead of one single bit like a normal D flip-flop. So every time the clock trigger, you shift the whole 4-bit from D to Q. It's pretty easy. So you can check for your clock edge, and every time the clock edge comes, you shift D to Q. Then you can end the module. But there's also another way, okay, maybe some of you might be interested. So instead of doing every single thing at once like this, you can actually make a for loop statement. Okay, so first in order to do that, I can create a parameter. I call it bit width equal 3. So I can now create my input and output. That's the same, right? It's the 3-bit. I mean, it's the 4-bit D, 4-bit Q. Then I scan for the clock edge. So I can run the clock from 0 to 3. Okay, so I just put the I in the QI and DI here to shift it, and module. Okay, so for loop also a legal thing in Verilog, so we can try to make use